Hey YouTubers, today, after 3 years, I finally get to work on my dad's 1977 Crescent Limited steam locomotive.
More than 100 pounds, my friend.
My dad had two Lionel train sets. He had the Spirit of 76 and the Crescent Limited passenger train set. Now as a kid, I remember my dad would always bring out the Spirit of 76 set. He would make up this big track layout set in the living room, and then for a few hours we would play with the train set. It was cool to see this long freight set just going around this big track, and I thought it was really cool. My dad rarely brought out this. He rarely brought out the Crescent Limited set for reasons I don't know why, but I remember it was only brought out 3 times. Now the third time that the Crescent was brought out was back in 1987. So the train was all set up onto the track, it was ready to go, and I remember that the locomotive would only go in reverse. Now for reasons not knowing why, the train set was just packed up and then put away along with the Spirit 76 in the basement for a very long time. Now my dad passed in 2018. And when he passed, I wanted to have the Crescent set for myself because I thought it was a nice looking steam train set and I really wanted to have it. So when I acquired the set, I wanted to give it its first maiden run. I had a small train table put up in the basement. I lubricated all the moving parts, greased up what I could, and when I let the train run, it did run, but it made this horrible squealing sound that I knew that there was something wrong. Now, what I remember is that my dad, when he put the trains away, he would keep them in their original boxes, which was good. He kept them in a humid basement, in a bigger box with a trash bag, up against the foundation of a basement. That's not a good recipe for preserving something. Plus, my dad highly neglected the trains when they were in storage for a long time. He never lubricated them, he never oiled, greased them, he never did anything. So the Crescent suffered heavily for that, and that's the reason why you heard all that squealing. So I went up online to research to see what I could do to fix up the steam engine, and I see that Lionel came out with like TMCC, command control, line chief, smoke blower units and stuff, and I'm like, this would be a great time right now to upgrade this locomotive to all this great technology. So in finding out what the problems are with this, we're going to upgrade the Crescent with TMCC upgrade, a new smoke blower unit. We're going to give a new paint job. We're going to update the graphics on this because the oil for the smoke fluid, it got on some of the graphics of the Crescent Limited logo. It kind of faded it a bit, and we're going to give some other cosmetic upgrades with this. So we're going to have this steam locomotive looking and running just like brand new. The first problem that I see is that the light bulb base has been melted onto the smoke unit frame. This has been running a little hot, and I figured the problem was the resistor or wiring in the smoke unit. So once I cut the wire to the resistor, the train did start to run a lot better once the power was cut to it. So it reduced the short and amperage going to the train. The Pullmor motor sits here, and if we turn this around, we can see the back of the armature coming through this plate. Now if I bring the camera in a bit closer, let it focus. If I take my needle nose, besides going back and forth, that's normal, but if it could be seen on camera, you could see that the armature moves up and down freely, and I believe that this is what was causing the squealing sound, and this is the reason why you heard that, and this is due to lack of lubrication onto the engine. Took the E unit off the motor frame, and if we look underneath, we can see the rotating drum and the solenoid that controls forward, neutral, and reverse. And if you look closely enough, let it focus, there's no grabber that rotates the drum for forward, neutral, and reverse. It broke off. So this is the reason why the engine always went in reverse back in 1987. Got a missing screw on the drive shaft, and we also have some cracks on the wheels. Okay, the inside of the tender, just have a basic, looks like electronic board here with a paper speaker. This is still the original stuff, and looking on the circuit board, it looks like there's either rust or mud, or I don't know what's going on with this, but it just doesn't look right. I did get this soundboard working only one time, and one time only within the recent few months, just to see if it even still worked. So here's a small clip of that. Then after that, it stopped working, even though I did put these few layers of double-sided tape underneath it, but I didn't want to give it a total clean, in case if I put all this work into it and then it didn't work anymore. So this is all going to get replaced. Before we begin tearing down the locomotive, it is best if we try to acquire the parts breakdown list. This will help us get replacement parts as well as rebuild the locomotive. Also, the parts replacement list part numbers. I got my AC commander from the Electric Railroad Company, also known as ThirdRail.com, and this is a very nicely put together set of instructions on how to install the AC commander into any AC driven locomotive. This I would recommend to read a few times just so that you would have the best understanding on how to install this, or else you will fry the board. Also from the Electric Railroad Company, the medium steam sounds for my Crescent Limited. This is a nicely put together set of instructions, and again, read everything because there is TMCC operation as well as conventional running for the steam sounds. A lot of diagrams and a lot of pictures, so again, read thoroughly. our megger has found an issue, and for those of you that know what a megger is from my videos, that's great. If this is your first time hearing about it, a megger is a device that puts at 1000 volts DC, and it measures the insulation value resistance of your coils and transformers and motors. So I'm going to explain this in every video because it could be somebody's first time hearing about it. Now, here's the E unit from the Crescent Limited. So the megger measures the resistance of this red stuff coated onto the copper wire. This way it tells us that if there's any shorts or anything inside of it, and that these guys operate at their full capacity. Now, setting them up is completely different from an ohm meter. An ohm meter, here's the field for the Crescent. So just for a regular ohm meter, we just take the two wires, the two leads from the meter, and you put on the two wires just to get the wire resistance. That's good. But for a megger, it's completely different. And you take the two clips. For this model, the clips are magnetic, so we put one on the metal frame, and then we take the other clip and we put it on one of the wires. Make sure that it is not connected to the grounding frame, or else it'll read a dead short. Then once you push this red button, the green LED and the on here will come on, and you'll see if there's any values in here. It'll tell you whether it's good, caution, it might be going, or that it is completely bad. I would not push the button while holding this because you can get a shock. So right now the item in question is the armature, because it is reading bad. So we have a short somewhere inside. So every time I went to run the train, I try and lube it, see what I could do to try and fix it up. I always had to clean the commutators on this because they're always black, and I had to do this for every run every single time. So something was not right with this motor. So nothing more than a simple cleaning with WD-40 and the Dremel tool with a felt wheel, and it got the commutator plates shining just like gold. So what would cause this motor to short out internally? Well, I went online and I found the first edition J.L. Cohen's post-war Lionel trains O-gauge reference manual 1 for steamers, diesels, and electrics. In here, this gives a lot of information on how to rewind your motors, fields, what gauge wires, relays, horns, and for a lot of different motors and different engine types, motor types, build types. There's a lot of information here that's completely invaluable. So on section 12-8, commutator shorted to shaft. It's a condition caused by years of heat, oil, and lubricant contaminants attacking the bonding agent insulation under the commutator bars. As before, this occurs when brush material in the slits combines with the lubricant which has been applied at the commutator end of the shaft. The concoction, when exposed to heat generated by the brushes, eats into the insulation between the commutator bars and the commutator backing, renders it conductive, allows current to flow from the bars directly to the shaft. At this point, one or more bars may become electrically connected to the shaft or of the armature, and of course to the other bars of the commutator. When cold, the resistance may exceed the high-end detection range of your multimeter. However, when powered up and exposed to heat, the concoction rapidly reliquefies and its resistance quickly drops, as described in the bar-to-bar short paragraph above. So again, this book here is very valuable, and we are going to have to rebuild this motor. So we're going to show you a little troubleshooting procedure for this, how we can get our readings to find out that it is shorted, besides using the megger. Before we begin any kind of troubleshooting, we should find out what kind of motor is inside the 8702. So we're going to look into the manual, find out what's in there. So let's see. Chapter 2, steamers. Motor assemblies. Let's see. Scout motors, metal scout motors, diesel electric motors, 200, 600 series power trucks, reverse units, horns, relays, couplers. Okay, part number indexes. Unit number index. Okay, this might be something I'm looking for. Unit number index. Well, I see my New York Central's in here. Okay, I don't see the 8702 in here, so Maybe could be under motor assemblies, I'm not sure. So I did an internet search on the motor type for the Crescent Limited, and I got on to Google, looked it up, and on trains.com, that's Z for trains.com, I found a little history from the 8702 from the MPC era. So let's look here, and number 8600 New York Central 464. Okay. The 1976 catalog featured top-of-the-line sets called the Empire State Express, headed by another New York Central 464 number 8600. However, this engine was not a repeat of the 8206. The 464 used a boiler casting from the post-war era 2046/646 engines, which were bigger, chunkier looking than the 665 design used on the 8206. The 8600 had smoke unit, magnet traction, and electronic sound of steam. Okay. So as I scroll down through the page, I got the Crescent Limited here, number 8702, and says here, until 1977, MPC era steam engines shared the same color characteristic of their post-war ancestors, black. That changed in 1977 when Lionel announced the Southern Crescent passenger set headed by a green, silver, and gold 464, using the same design as the 8600 from the previous year. The 8702 also featured smoke, magnet traction, and electronic sound of steam. So I think we have a little history here on the 8702. So if the 8702 is like the 8600, we're going to see that it uses the post-war era 2046 motor. So we'll put this aside. Let's go to the book here. Look for the 2046 design. I see it's in here. That's section 2, chapter 2, section 52. And this is the beginning of it right here. Chapter 2, page 50, section 52. The 2046-100 motor assembly. And as we go to the next page, 2-53. Here it is. I have the armature dimensions, wire type, gauge, resistance, and how the motor is going to be wound, including its field. Okay, so we're going to get some readings here off the commutator plates, and between the commutator plates 1, 2, and 3, anyone measured in between should measure between 1.5 to 1.7 ohms of resistance. Now, you also have to figure in your conditions in your home, that when you're doing testing, that the measurements may be slightly off. Okay, so this one here is 1.8 ohms, 1.7. This one here is 1.7 ohms. And this here also 1.7 ohms. All right, perfect. So we are in the range with the 2046 motor specifications. Now, if we go to where the armature is, we're going to turn up our resistance reading. So we're going to put one probe on the shaft. We're going to put one here on the commutator plate. We get a better grip. Any commutator plate, doesn't matter. Alright, so it's showing open right now, but we're going to increase that reading. No, nothing yet. Let's go a little higher. 2000 mega ohms. There we go. This reading right now between the armature shaft and the commutator plate, this should read infinitely open. And we're getting a reading of 86 mega ohms. So this may be a high resistance reading, but as they stated, that as this heats up, this resistance reading goes down dramatically, getting current right down to the armature shaft. Before we tear this armature apart, we need to understand how it was first built. So according to Robert Hannons' guide, the wire size is 27 gauge with 77 turns. The turns are going to be layered, and there's going to be 6 layers with a clockwise direction for each wind. The resistance is 1.5 to 1.7 ohms, which we already measured, and the tie-off is going to be common. Now what that means is that each of these windings here is going to be tied together and hidden underneath the commutator plates. And typically you will see other armatures where they are wound clockwise or counterclockwise, then they're tied to the commutator plate, then they're wound again to the next part of the armature, then brought to the commutator plate and soldered, and so forth. So this one has a common tie-off, and if you look right inside of here in the motor, you can see that the wires are twisted and soldered together. Now to identify the winding of this, turn it upside down with the gear facing up, and if we look where the wire comes in, this here shows that it's counterclockwise, while in the book it shows clockwise. I guess if we went with a clockwise position, the motor would just run in the opposite direction that it was intended to do. So I'm going to stick with the clockwise position as it shows here in the book, since it is part of the 2046 design. So to get started, we're going to remove this wire up here on the commutator plate, and it looks like that it is wrapped around, so I don't think I'm going to be able to unsolder that, but I'm going to cut the wire, and we're going to start here at this corner, and then we're going to count the number of winds as we go around to see if we get 77 turns in this part of the motor. So for every time we pass this one section, it's going to count as 1 turn. Before we take off any of this wire, we should figure out how much wire we are going to need to rewind this. So I have a digital caliper, and we're going to measure the outside area of the wire. So on the thickest part, it's 0.52 inches, so it's 0.52 and 52 here. Then we'll measure this width right here. So that would be 0.63 on top and 0.63 on the bottom. With our measurements with the caliper here as shown, one wrap of the wire around the armature is 2.30 inches. And if we multiply that by 77 turns, and with doing all this math as shown, it comes down to 14.75 feet of 27 gauge wire. Now obviously we're not going to use that much wire, because as we take the wire out, this area of the wire is going to get smaller and smaller as we get down more into the armature. So we can go by this measurement and go by a roll of wire, or we could just unwind this whole thing and just measure the wire that way. One, 2, 73 turns later, 75, 76, 77. Yep, just what I thought. Perfect. Perfectly described in Robert Hannons' book. Excellent. And here I can see the tie-off, the common tie-off inside the armature. And it's right there, exactly how it was described in the book. So we're going to do this for all 3 of these armature pieces here to get this wire out. And I'm going to see if I could try and take off the commutator plates just to make this guy easier to rewind. So let's see if I can find that tip out, so I can show that to you before you do your own motor rewind. Okay, so as I am continuing to unwind the magnetic wire from the armature, I have already undone 2 spools, and I figured let me do a meg test anyway. So as I pulled the wire out, I did a meg test. Whatever the short was, it's now gone. Now as I did the second spool on this side, some areas of this magnetic wire was very hard to pull off, like it was being pinched right here on the sides of this corner. So I think that this is where the short was coming from, that this corner piece was digging into the insulation. Either way, this is still going to get rewound with new wire so that we can correct any issues that this armature has. And the commutator plates, They just come right off. Before I rewind this armature, I'm going to inspect it just to make sure that there's no cracks or anything on the plastic which may hinder my installation. So I'm just giving a quick overview just to see if there's any imperfections or anything here that may stop me from rewinding this. And just at a glance, I mean, everything does look pretty good. I'm also going to give this a little cleaning just to get off any oil that I installed, as well as any carbon which may have come from the brushes. Now, before I do rewind this, I still have the issue with the squealing from the rear gear plates and the brush plate. So if I take the back here, the gear plate, armature plate, and I just put it on here, you can see that there is play on this. Now, I don't know if this is how Lionel intended to make this, or this is just from not lubricating the back shaft area, but this is a good reason for why it could have been squealing. Also, if we look at the brush plate, and by the way, the shaft here from end to end is all the same size diameter. If I put this in, that is just way too much play. I mean, I imagine that this would have to be a lot stiffer just so that this motor would not vibrate in the motor housing. Now, I have worked on my Pullmor motors in my 75th, 90th anniversary sets, the Conrail rectifier, the chassis system SD40s. And anytime I pulled out the Pullmor motors, you had to take these brush plates and you had to put them in straight on top of the motor so that it would seat in there just right. And they were very tight in tolerances. So one way that I could get this fixed is if I go to eBay or somewhere and just get new pieces, quote unquote new pieces, but I'm running the risk that these parts are going to be worn too. So I'm going to install ball bearings into the brush plate and into the gear plate. For me to choose a ball bearing size, I have to first look at the brush plate, and if I take my caliper, the inside area from brush to brush is 8.5 millimeters. And if we look at the shaft size of the armature, this is 3 millimeters in diameter. So with some research, I did go on the internet and I did find a ball bearing that is 3 millimeters inner diameter, double sealed with a 6 millimeter outer diameter. With this ball bearing, we're going to have to make this fitted onto the shaft of the armature. Now in this size here, we just try and get it on here, but because the shaft is 3 millimeters and the ball bearing inner diameter is also 3 millimeters, I mean, I'm pushing right now, and it's not going to go on because it's like right at that same measurement. Now, however, we can get this on, but I did it to this end of the armature. So take the ball bearing, and there we go. So how did I get this ball bearing on? Well, I'll show you, and it's very simple. Take a cordless drill and install your armature into the chuck. Make sure that the chuck is not too tight, and once installed, just give the armature a few spins. We want to make sure that this end of the armature is not spinning around or spiraling in any way, because it will affect the sanding procedure. Next, take a sponge, some 150 or 200 grit sandpaper, and we're going to place the edge of the sandpaper right by the edge of the sponge, just like so. Now we're going to take the drill and give light pressure on the armature on the sandpaper, and then we're going to start sanding away the shaft of the armature like so. The best thing you want to do is to keep even pressure on the armature shaft, so this way it sands evenly. If we were to take this by hand and wrap this around like so, our fingertips are going to give uneven pressure on the armature shaft, and this will not sand evenly. Every so often, just to polish it up, I use 1000 grit sandpaper, and this I could just do at the, and this I could just wrap around the armature shaft just for a moment, just to clean it up a little bit, and then every so often trial fit the ball bearing onto the edge of the armature shaft. The magnetic wire I have chosen for this project is from Temco Industrial. I'll measure out 3 lengths each at 14 feet long. I will use a razor knife to scrape off the enamel on one end, about an inch, inch and a half or so, and I will twist the wires together for conductivity for this motor. This drawing represents our 3 magnetic 27 gauge wires that are ran to rebuild our armature, and they all get tied together at a common tie point. Now I made them each 14 feet long. It is longer than usual, but figured that, hey, longer is better, especially when you have to rebuild a motor, because it is more costly if you have to cut more wire and then redo it again. So a little longer never hurts. So we want to make sure that all of these wires here are going to have some form of resistance between them before we solder anything together. Now, once you have everything here stripped, you have all these wires twisted together. At the other ends, just strip off about an inch or so just to expose the copper. And I have them labeled A, B, and C, or you could do 1, 2, 3, it doesn't matter. Take your digital multimeter, set the resistance in ohms, and you're going to measure the resistance between wires A to B, A to C, and B to C. Now, being that in Robert Hannons' book it says to use 27 gauge wire, which is what I did, and I am getting the readings between 1.9 and 1.7 ohms, either between the letters here shown in this drawing. So far we're on the right track of rebuilding this motor. Once I'm sure that these wires are making connection, I will solder them together. Just a simple bead at the end of the wire will do it. Somehow you just cannot solder these wires together. Once your wires are soldered together, just recheck the readings at your 3 points to make sure that they are still giving you the same resistance readings. Then I will install a heat shrink tube to cover up any potential sharp ends on the soldered area. Just before I unwound this motor fully, I took pictures of it as a reference for reassembly. So now with the armature fully cleaned, we can take this magnetic wire and we're going to start winding it around our armature. Now, according to this here, we're going to start from the inside here of our segment, and then we're going to work our way back out and then back in again. And according to Robert Hannons' book, there's supposed to be 6 layers per segment here on the armature. So, if I go back to my photo, we can take our common tie off, place it close to the armature shaft, and start wrapping around one of these segments. I'm very excited about this, so can't wait to see how my first motor rewind goes. Okay, so 1, 2, 229 excited turns later. Okay, so now my armature is fully rewound. I did each segment one at a time, and I put a piece of scotch tape on the windings so that they would not come undone. Each segment does have 77 turns on it. 6 layers I'm not sure about, but I did my best to rewind this armature and everything. It does put a test on your eyes when you are rewinding this, because you're not sure if you're putting too much wire in one area or not. So when I was done, I did leave some wire out from this, but this is what was left after I cut the end off here. I mean, I did have about almost 2 feet of wire sticking off from this, so, you know, I did over measure in case I messed up somewhere. So I have enough wire here to go on to my commutator plate. So next up is to install this commutator plate, which was on the armature, but the problem with this that it was warped, and I don't think I can use this. So I went out and I got another one. a successful first run, let's see how strong this motor unit is with its new earth magnets. Let's see it pull a freight train. It's not even slipping. So, I have fully rebuilt the motor unit for the Crescent Limited, with the exception of the field windings, which I have not touched. I have rebuilt the armature, I've added a new commutator plate, added ball bearings to the brush plate and gear plate. I have replaced the wheel gears and added rare earth magnets for the magnet traction. Now this project has given me so much more confidence and hope that I can complete this project as I see envisioned in my mind, and I can't wait to progress with this and get it finished. However, I do have some smaller projects I'd like to tackle as well, so I'm going to do those in between as I'm working on the Crescent Limited. So as I get work done, I will post those videos when I can. Now I just want to talk a little bit about the rare earth magnets for the motor unit. Lionel made some basic, I guess, ceramic magnets for their magnet traction, and it did its purpose for the time being, but after this time the magnets, they lost their power. So I wanted to try rare earth magnets. So you're going to need to find a magnet that has a north pole and a south pole on the ends of the walls of the of your motor frames. If you were to have like a north pole, south pole here, and then match it up against the motor frame, the magnet traction will not work. So you're going to have to experiment with the magnets with this. So the magnets I chose for this was 3/8 of an inch by 1/2 inch by 1/16 of an inch thick. And I've chosen that size because the wheels were able to move freely. You can add more magnets onto those magnets as well and increase the power. However, the rule of thumb of this is what I would state. If you're able to push the motor unit back and forth and the wheels are able to move, then you have proper magnet power on the wheels for the magnet traction. If your wheels are not moving as easy and it takes a little more power to get them going, but you possibly have too much magnet power on there, and it's going to take more energy for the motor to move your engine than it would to move the train. So again, experiment with it a little bit. Now, also with the gear plate, I do have the ball bearing attached onto there. The gear on the armature does rest upon the gear plate, and that has to be lubricated as well so that the engine runs properly. So, since I drilled out the gear plate, I had to add a PTFE washer onto that, which is high temperature rated, and it's also a very slippery item. That washer is 3.18 millimeters in diameter by 7 millimeters. I had to shave it down and place that over the washer inside of the gear plate. Plus the washer, plus the ball bearing was recessed a little bit into the gear plate so that the PTFE washer can sit right on top of that and make a smooth surface for the gear to ride on the gear plate. So I'd like to thank everybody for watching the video. I do try and make the videos as detailed as I can. The problem is they are a little bit long, but they are informative. So this way you would have no doubts or anything when you do your own Lionel projects. So again, leave comments in the comments section. I will answer them to the best I can. And as always, I'll see you around on the next project.